Alright, so today we're going to talk about measures of variability. And basically what you have here is a data set. Say you have measurements 90, 85, 65, 75, 70 and 95. So how do we measure how variable this data set is? Remember, in the previous video we talked about how do we find the average for this data set, and we talked about three ways to finding the average: the sample mean, the sample median, and the sample mode. In this one here, we're going to talk about variability, how close or how far those numbers are away from each other. So in general, however, we describe the data set by the values, any data set as x1. So this is our sample here. We can talk about this sample here, and our values are x1, x2 up to xn, and so we have n measurements, or a sample of size n. So the simplest way to measure data variability or dispersion is to take the range, which means take the largest measurement minus the smallest measurement. Or we can write it simply as, the range is equal to the maximum minus the minimum. So in this example we have here, where our data is this set, if you want to find the range, we have it's the max minus the min. So the largest value here is 95, the smallest value is 65, and so the difference is 30. The second method, this method, of course, sometimes if all your measurements were in this area and you have another measurements which is 10, then you'll have a very large range, but you know all your values except one are very close to each other. So this sometimes doesn't work well to measure data variability. So here is another method. It's called the mean absolute deviation, and basically what we're going to do is to measure the distance between each of the measurements in this sample x and the average. So we take the distance between each value and the average, and of course to make it a distance we need the absolute value. We sum, remember we talked about the summation sign, we sum those distances and we divide by how many measurements we have. So let's apply this to the problem we had for this data set, and now we're going to list those measurements, column x here, in here. So I have 90, 85, 65, 75, 70 and 95, and of course if I sum all of these it's 480. So, and if I divide by n, which is 1, 2, 3, 4, 5, 6, that's going to give me an average of 80. Right? So we know that much. So then so first I want to find how far is 90 from 80. It's 10, and we called that x minus x bar. 85 minus 80 is 5, 65 minus 80 is negative 15. But that's not a distance, so we're going to change this into a positive value, and that's where we use the absolute value. So change the negative value to a positive value. Same thing here, 75 minus 80 is negative 5, so we change that to 5 using the absolute value, and so on. Remember, the sum here is always 0 because you have measurements on either side of x bar, while here it's 60, the total. So we add all of these, 10, 5, 15, 5, 10 and 15, that adds up to 60, and then we divide by n, which is 6, and that gives us a mean absolute deviation which is equal to 10. And so here's a comment about using formulas. Again, this is very important when you do the calculation, that you put it in the form of a formula. You have the mean absolute deviation equal, first you write down the formula, then you substitute. So we have calculated this quantity, which is this. So this is this quantity here, 60, and n is 6, which is how many we had, and then we got the answer, which is 10. Okay, because the mean absolute deviation is a good measure of variability, because it just gives us the average distance from the mean. But it's really difficult for mathematical manipulation, especially that we have absolute values. So instead of, so basically we wanted to change those values to positive, and one way is to take absolute values. What would be another way to measure those distances, but without using absolute value? You can't keep them the way they were because we have those negative numbers. So another way here is, instead of taking absolute value, let's square each one of these numbers. So the simple idea, and this is the simple idea here, is to take x minus x bar, what we did up there. Instead of taking absolute value, we square. So these deviations, we call them deviations, deviation from the mean, sample mean, is squared. We add them up all together, and then we divide by their number minus 1. We'll talk about why we divide by minus 1 in a minute. And we get s squared, which is called the variance. So why do we subtract by n minus 1 and not n? Well, now that's going to bring us to talking about samples and populations. Remember, we talked before about a sample and a population. And although this is not working, the data we have is about, we have data from the sample. We are interested in the population, and so we want to make inferences about the population. The x bar we are using here is not a population x bar, it's the sample x bar, and so there's a penalty for using an estimate of the mean instead of using the population mean, and that penalty is to subtract 1 from here. You get n minus 1. And so if you notice this one here, this, because we subtracted by n minus 1, so instead of 6 we divide by 5, this tends to be a little bit larger than it would have if we had population mean, and that accounts for that not knowing the actual mean. And we call the sample variance s square, right? So once you get that, it's easy to move to the sample standard deviation. Well, the idea, when we square these numbers, they're going to get very large. So to account for that, to get something that would be of the order of this, we take the square root, right? And that's basically what the standard deviation is, which we will use quite frequently. So this is the most used measure of deviation, is the sample standard deviation. And just before we move on, remember, keep this in mind, that the mean absolute deviation is a very good measure of variability. It's equal to 10, but we don't like it because it's not gonna, we're not gonna be able to manipulate it to get our data summary, good data, manipulate the data summaries later. So let's go back, use the same sample we had, take x minus x bar, but now instead of taking absolute value, let's square. So the 10 becomes 100, 5, 25, 15, 225, and so on. So we add, we got 700. Therefore, and we have the summaries here, x bar is equal 80. We did this. S square now, the numerator is the sum of x minus x bar square, and here we have x minus x bar square. We have each one of the measurements. We sum them to get 700, so that's where the 700 comes from. It comes from here. And now we divide by n minus 1, which is 6 minus 1, 5. This gives me 140, which is way bigger than the 10 I had before with mean absolute deviation. So if I take the square root of this quantity here, that's the square root of the sample variance, I got the square root of 140, 11.83, which is comparable to what we had before in the sample mean absolute deviation. Okay, so that's the idea of this. Now, quite often, if you get a mean here, which is say 80.235, this calculation would be very difficult because now 90 minus 80.235 is going to be 9 point whatever and so on. So it's going to be complicated, and it will cause in general round off error. So we're going to take those formulas, manipulate them algebraically, and come up with more useful formulas for calculation. So these are computational formulas for S square and S. They are the same as the ones we had up, but if we put them in this form, they're going to be much more useful for computations. And I wanted everybody to recall, some books call them shortcut formulas. Actually, they are not shortcut formulas, they are just computationally more stable formulas. Okay, and in this way, if you look at this formula here and you start here, you always start inside, so that you take each measurement you have, you square it, you add them up. You take each measurement here, you add them up, then you square, you divide by n, and then you divide everything by n minus 1, and that gives you your sample variance. Again, this sounds easier if your numbers are small and you don't have fractions or decimal points, but in general this is much more efficient for computations. And of course you take the square root of it to get the sample standard deviation. Here's an example. I'll give you another example here. So you only need, and you don't need x bar in this case, you just x and x squared. I have the same values, x and their total. I square x, 90 square, so dealing with large numbers here, I get this number. 85 square, I get this value. 65 square, I get this one, and then I add them up. So now again I have write down my formula. So this is my formula here, first written down, and then I want to substitute in it after I get this summary. And you notice sigma x squared, that's the where you square each one, you add them up, that's 39,100. That's sigma x, the sum of all these values is 480. You square, divide by 6, and then divide everything by 5. And now we did the substitution here. Let's simplify. So the first one is 39,100 minus 38,400. That's this squared over 6 gives me this. And the difference is 700, which is what we had before. So that gives me exactly, and then I divide by 5 and get 140, and this standard deviation is 11.83. You should be able to do your analysis either way. This is going to be the end of this video, because next video will talk about the relationship between these measures and their population counterparts. And see you in the next video. Bye.